A plane may be determined by the points and lines. Okay, so what information is required to completely define a plane? A plane, first of all, is the set of all points in a flat sheet. So a plane has two dimensions, but it exists in three space. And if you take two lines and cross them, non-collinear lines, and cross them, they will define a plane. That's this one down here. You take 3 points. If you think about 3 points being stretched out between three people, let's say holding a sheet of cloth or something, they would hold it tightly. Three people would define a plane. Two lines that are parallel but not coincident. You think of a sheet being stretched across two rods, perhaps. And finally, material wrapped around a rod or a line being pulled at from some other point that is not on the line would define a plane, and that's this case here. So, four situations where information are provided and is sufficient to define a plane. Now, the vector equation of a plane is very similar to the equation of a line with one added thing. You still have R naught, which takes you from the origin to the plane. So P naught is on the plane, and R naught takes you from the origin to the plane. And then to get any other point on the plane, one vector is insufficient. You have to have a second vector, we usually call it V, that is not collinear to you, that, some combination of U and V can take you from P naught to P. So that's the vector equation of a plane. So very similar development as we had for the vector equation. And I just sort of talked about it. And there's the equation. The plane, pi, right? Pi for plane, is R is equal to R naught plus SU plus TV. So a plane pi is given by the following vector equation: 2 points on the plane. S equals 0 and T is equal to 0. So obviously -1, 0, and 2 are on the plane. Okay, R naught goes to P naught. P naught is on the plane. Another one, let S equal 1 and T equal 2. Why that? Why not? I guess. R would be equal to -1, 0, 2 plus 1, 0, 0, 1 plus 2, 1, 0, -1. And that gives us 1, 0, 1. So 1, 0, 1 would be on the plane. Okay. Find one line on this plane. Okay, we need R naught and one direction vector, so one line on the plane. We have -1, 0, and 2 is on the plane, and one direction vector. There we go. That's a line within the plane. I could have taken the other direction vector. It would also have been a line in the plane. Find the vector equation of a line perpendicular, passes through the origin, and is perpendicular. So line perpendicular plane. So the line has to be perpendicular to both direction vectors. How do we get a direction vector or a vector that's perpendicular to two other vectors? Well, that sounds like cross product. So we cross U and V, right? We cross U and V. Remember how to do cross product. We list the elements of U, the elements of V, or the first one, -1, 0 to -0, so 0, 1 minus 0, and 0 minus 0. Oops, that was supposed to be 1. So the direction vector for this line, the line perpendicular, is 0, 1, 0, and it has to go through the origin, so R naught is 0, 0, 0. Okay, so the line is R is equal to R naught. I don't have to write the 0 vector, plus T 0, 1, 0, where that's a different T than I had that. I could have used a different parameter. I don't want to confuse things. This is an extra example, so you have to make a note. Is 0, 0, 0 on the plane? So does OA belong on this, lead you to a point on the plane? So what we have is we have to check that this is true, or it's possible that 0, 0, 0 is on the plane. So I'm going to subtract R naught from both sides. That gives me 1, 0, negative 2. And it's a little more complicated than checking for a point on a line because we have two direction vectors. So if we look at the x parametrics here, the x part of it, if you like, 1 is equal to 0s plus 1t. So we have t is equal to 1. Well, that's easy. Y, we have 0 is equal to 0s plus 0t. So that's fine. That's true. That works for any s or t value. So finally for z, we have negative 2 is equal to 1s minus t. Well, we plug in, change colors. We plug in, we have negative 2 is equal to s minus 1. So s is equal to negative 1. Yes, a is an element of the plane when s is equal to negative 1 and t is equal to 1. All right. All right. Next part. Going to the parametric equation of a plane. And as you might expect, you just find the individual parameters. So x is equal to x naught plus SUX and TUV, right? That gives you that. And I'll just go through it. Y is equal to Y naught, SUY, TUV, TVY. And finally, Z naught, SUZ, and TVZ, right there. So parametric, very similar to the parametric equation of a line. And then down in red, I added something in. So can symmetric equations be found for a plane? Remember, symmetric equations, we solved for the parameter. We solved for t, the scalar parameter. We have both s and t. So no, there is no. It's not possible. There's no symmetric equation for a plane. It's only for a line in 2 space and for 3 space. Convert the vector equation to the parametric equation. Okay, so x, negative 1, no s's, 0s, I'm not going to write that, and 1t. The y is 0 plus 1s minus 2t, and the z is 2 minus s and no t's. That's it. Convert the parametric equations to the vector equation. Okay. So we need the constants for the x, 1, nothing for the y, so 0 and 4. It looks like we have s and t, so I'll put s, I'll put t. For the x, we have 1s and 2, negative 2t's. For the y, we don't have any s's, but we have 3 t's. And for the z, we have negative 1 s's and no t's. So there it is. Example 4. Now we're going to go through the 4 different situations that there was in the introduction. 4 ways of being given the information. We're supposed to come up with the vector equation of the plane that passes through the points. We're given 3 points. So we need R naught, we need U, and we need V. Right? R naught can go from the origin to any point. So we can use OA. We could use any of them, but OA is as good as any. There we go. V has to be a direction vector that is in the plane. So those 3 points are in the plane. So we can just do AB, which is OB minus OA. So 2 minus 2 plus 1. In V, we can do, I don't know, A to C. So that's OC minus OA. So 0, minus 1, and 2. So then the vector equation of the line, R naught. The only thing you really need to be careful of is that the information is valid. If you look at the two direction vectors, they're not linear, okay? So that would be the only concern that you might have. All good with that? Okay, next example, example 5. Two parallel and distinct lines. So look at those lines. And it seems pretty obvious that we have an R naught. We can use one of the ones from either of the lines. So we'll just take the first line. And we have a direction vector. And you see that those two direction vectors are scalar multiples. You multiply the first one by -1, you get the second one. So we just use one of them. I'll use the one that's all positive. It doesn't matter. But V is the question mark. Okay. And this is the way I think of it. Let's say we have line 1. So I'm just going to try to illustrate it in 2 space. We have line 1 and line 2, and they're parallel. And we have P0 1 and P0 2, right? And we have, I'll use a different color. We have vector U and we have vector U. They're the same, they're opposite, doesn't matter, but they're along there. We need another direction vector that's in the plane that contains those two lines. Well, the simplest one I can think of is the one connecting the two. So V, I'm going to use V to be P0 2 minus P0 1. And so that's 3, 4, 0 minus 1, 2, 1. Well, that's O. Right? So that's 2, 2, and -1. So R is equal to 1, 2, 1 plus S, 0, 1, 2 plus T, 2, 2, and -1. That's one way to think of it. Just as easy as anything else. Let's see. We did the vector equation. Then went to parametrics too, so let's do that. 1 plus 2t, 2 plus s plus 2t, and z is 1 plus 2s minus t. So there's the parametric, the vector, and here's the parametric. Example 6, determine by two intersecting lines. So all the points on both lines are on the plane. Both direction vectors are in the plane. So the simplest thing is just to take parts of everything. So R naught from the first one is as good as the second. I could use the second R naught, that would have been fine. And I can use the first vector portion and the second one. They're not parallel, so that's all good. That's it. It's literally as simple as that. Okay, I'm just looking at a write-up I had of this example. And they actually went through the effort of verifying that there's a point of intersection. That's actually not necessary if they tell you those lines intersect to form a plane. If they don't, then you would have to check. But it doesn't ask us for that, so it's not required. Example 7, plane determined by a line and an external point. So this line is in there. We need another direction vector. That's what we're missing. So, it's going to go to the origin. So, just to make it simple, here's R naught, and we'll keep that first direction vector. We know the direction vector is the plane. Well, to be quite honest, we don't need that because it contains the origin, and we can just make that the parameter. a direction vector from the origin to another point, as long as they're not parallel. So I'm just going to clean that up. We usually put S first, so I'll do that. If it wasn't the origin, then it would be a little more work, but that makes it pretty simple. Okay, I said there was an additional example, so here it is. Copy it down. So this is to improve your spatial reasoning. We spend a lot of time, if we were in the classroom, talking about visualizing things. So unfortunately, that's sort of harder. Find the x-intercept for the plane. The x-intercept happens when y is equal to 0 and z is equal to 0. So we have the point, we'll call it x, 0, 0. We're trying to find what x is. Well, from the origin of that point has to be on the plane, right? If it's the x-intercept of the plane. So what I'm saying is I can just sub that vector in to the plane. Now what? Well, I'll simplify a little bit. I'm going to subtract that R naught value. So I have x minus 2, negative 3, negative 4. And you've sort of seen this sort of setup a few times now. We'll do the x parametric if you like here. X minus 2 is equal to s minus 3t. The y part of this is negative 3 is 2s minus 2t. And for the z, I have negative 4 is equal to 3s minus t. It should be solvable because there are 3 variables and 3 equations. I'm going to use the y and z equation. Let me number them up. 1, 2, and 3. I'm going to use 2 and 3 to solve for s and t, and then use that to get x. So just looking at this, I'm going to take equation 2 and subtract 2 equations 3. Okay, because that's negative 2 minus negative 2t. So that will cancel out the t's, leaving me with s's. So negative 3 plus 8 is 5. 2 minus 6 is negative 3. And s is equal to negative 5/3. No, not 3. 2 minus 6 is negative 4s. So s is equal to negative 5/4. All right, I need to solve for t still. Okay, sub s into, guess it doesn't matter. I'll do 3. Negative 4 is equal to 3 times negative 5/4 minus t. So that's negative 16/4 plus 15/4 to negative t. T is equal to 1/4. And I'm running out of room. I don't want to go to another page. So let's look at equation 1. X minus 2 is equal to negative 5/4 minus 3 times 1/4. Oh, that works out. X minus 2 is equal to negative 8/4. And x, oh, look at that. Isn't that cute? So I'll just put up the answer up here. The origin is the x-intercept. It's also the y-intercept and the z-intercept, but there we go. That's it for this lesson.